Hi all, welcome back to my video tutorials, and this video is based on Booth multiplication algorithm. This is the flowchart representation of this Booth algorithm. So first this indicate the initialization part of Booth algorithm. First initialize an array M with the value multiplicand and another array Q is initialized with multiplier. Q0 bit is initialized with value 0 and an accumulator array A is initialized with full of zeros. And N indicates number of bits in the multiplicand or multiplier. So put the full multiplicand binary representation in array M, multiplier bits in array Q, and accumulator array put full of n zeros initially. So then consider the value of the combination bits Q1 and Q0. If it is 0, 1, then perform A equal to A plus M. If this combination Q1, Q0 is 1, 0, then perform A equal to A minus M. That is, accumulator array is replaced with a new value A plus multiplicand value when if the Q1, Q0 value is 0, 1. If this Q1, Q0 value is 1, 0, then replace the accumulator array value with a value A minus M. Okay, two more possibilities are there for this combination Q1 and Q0. If it is 0, 0 combination or 1, 1 combination, then directly perform an arithmetic right shift of arrays A, Q, Q0. Okay, if this combination is 0, 1, first perform this addition, then perform arithmetic right shift of array A, Q, Q0. If this combination is 1, 0, first perform this subtraction, then perform the arithmetic right shift of A, Q, Q0. Then decrement the value of n by 1. Okay, then check whether this n value is 0 or not. If it is 0, then we get or collect the result from the product of multiplication is obtained from the array combination A and Q. If it is no 0, then repeat the same cycles up to when this n becomes 0. When this n becomes 0, we get the result value from this array AQ. Okay, so we can consider one multiplication example, that is consider multiplicand bit is this one example. Keep this flowchart with this iteration steps. So refer this flowchart and iterate this example. Consider our number is multiplicand is minus 7 and the multiplier is positive 3. Then what will be the result of multiplication? Minus 7 into 3 is actually minus 21. We want to get the result minus 21 with this multiplication. So M is actually minus 7. How to represent this minus 7 in binary? So we need to consider the binary representation of 7 first. 7 in binary equal to, what's the binary representation of 7? 0, 1, 1, 1. Then minus 7 is actually 2's complement of this positive 7. That is 1, 0, 0, 0 plus 1. That is 1, 0, 0, 1. This is actually minus 7. Okay. Then binary representation of 3. Binary representation of 3. It's the binary representation of 3 in 4 bit 0, 0, 1, 1. Okay. These are, this is multiplicand and this is multiplicand. So consider this one array. N indicate number of bits. A is the accumulator array, Q is the multiplier, and Q0 is initialized with 0. Okay, based on this initialization, N is number of bit is actually 4 here. Okay, accumulator with full of 0. How many zeros? N number of zeros. 2, 3 and 4. Okay, Q means what? Multiplier. What is our multiplier? 3. 3 in binary is 0, 0, 1, 1. So 0, 0, 1, 1. Put this 0, 0, 1, 1 in this Q array. Then Q0. How to initialize Q0? With a 0. So just initialize 0 here. This is the initialization step. Okay. Then what's the next step? Check if this Q1, Q0 is 0, 1, 1, 0 or 0, 0 or 1, 1. This is Q0 bit. Here it is 0 and Q1 bit is this one. So consider this combination. Q1, Q0. This is actually Q1. This Q1, Q0 is 1, 0 here. If it is 1, 0, what's the next step? Perform A equal to A minus M. So perform next A equal to A minus M. Okay, so replace this array A value with new A minus 1 and A minus M value. Okay, so the bit is for itself. Then A. How to get this A equal to A minus M? A here is 0, 0, 0, 0. Minus M means what? Minus of minus M is minus of minus 7. Minus of minus 7 is actually positive 7. So A equal to A minus M means A equal to A plus minus M. Our M is actually minus 7. So minus of M means minus of minus 7 is actually 7. 7 in binary is 0, 1, 1, 1. So A equal to A minus M. How to perform this operation? A equal to 0, 0, 0, 0 plus minus M means this one. Add. It is 1, 1, 1, 0. Okay, so substitute this new value for array A, that is 0, 1, 1, 1. Just write down the 0, 0, 1, 1 and 0. Okay, what's the next operation? Next operation is arithmetic right shift of array A, Q, Q0. Okay, arithmetic. Next step is arithmetic right shift of array A, Q, Q0. Arithmetic right shift of these two array A, Q, Q0. So just write down this for directly there. Then perform arithmetic right shift. Arithmetic right shift means keep the first bit of A as such here, then perform one bit right. So this 0 comes here, this 1 comes here, this 1 comes here, and this 1 comes here, this 0 comes here, this 0 comes here, and this 1 comes here, and this 1 comes here. Okay, just neglect this or discard this Q0, previous Q0 value. Now this is the status of our different arrays. N having value 4, A having 0, 0, 1, 1, Q with 1, 0, 0, 1 and Q0, 1. How it get? This value is obtained after the 1 bit right shift or 1 bit arithmetic right shift operation of AQ Q0 array. Okay, how to perform this arithmetic right shift? Just keep this MSB value as such here, then perform 1 bit right shift. This 0 here, this 1 here, this 1 here, and this 1 here, 0 here, 0 here, this 1 here, and this 1 here, and discard the current value of Q0. Okay, what's the next step? Next step is n equal to n minus 1. Next is n equal to n minus 1. So reduce the value of n. Now it is 4, then reduce by 1, it is 3 now. Then put all the other values as such here. Okay. So complete one iteration. Right? Okay. Is this 3 is equal to 0 or not? This is the next condition checking. N is 3 now. It is not equal to 0. So we want to perform the same or repeat the same. Okay. So go to the first, this step, condition checking. Check the value of Q1, Q0 next. Here this 2. Okay, or this 2. This 2 is actually Q1 and Q0 value. Here it is 1, 1. If it is 1, 1, what is the next step? Next step is no need to perform addition, no need to perform subtraction. If it is 1, 1, directly perform arithmetic right shift of AQ, Q0. Okay, so next step is arithmetic right shift of arrays AQ, Q0. So keep this 3 as such here, then perform arithmetic right shift of these 3 arrays AQ, Q0. That is, keep this 0 as such here, 0 here, 0 here, 1 here. Okay, then this 1 comes here, this one here, 0, 0, and this one comes here, discard this 1. Now this is the status of our array AQ, Q0 now. Okay, and what is the next step? N equal to n minus 1. This is the next step, n equal to n minus 1. So reduce the value of n by n to 2. 2. Then write all other values just down here. Okay. So again completed the second iteration. Here again check if n is 0 or not. It is not 0 now. It is 2 now. So repeat the same cycle. Again check values. What's the step? Check value of Q1 and Q0. Here the Q1 and Q0 is 0, 1 now. If it is 0, 1, what we want to perform next? A equal to A plus 1. Next operation is A equal to A plus M. Okay. A equal to A plus M. So write this 2 directly down here. Then we want to substitute a new value for accumulator array. What is the new value? The value is A equal to A plus M. A is now 0, 0, 0, 1. M is actually our multiplicand. Multiplicand is minus 7 and minus 7's binary representation is 1, 0, 0, 1. Okay. So addition means just add this value with A. So add 0, 0, 0, 1 plus 1, 0, 0, 1. Addition means just add both multiplicand value and accumulator array. Okay, then 1, 1, this is 0, 1, 0, 1. 1, 0, 1, 0. Okay, so put this new value here 1, 0, 1, 0. And write this Q array value just down here. Okay, then put this one here. This is the current status of our different arrays. Okay, and what is the next operation? Our next operation is arithmetic. Next operation is arithmetic right shift of AQ, Q0. Is it right? Okay, then write this 2 here. Then keep this 1. Then perform 1 bit right shift. 1 0 1. Then this 0 here. 1 1 0 and this 0 comes here. Is it clear? Okay. Then what's the next step? Next step is n equal to n minus 1. Then this 2 become 1. Okay. Is it a 0? Is it a 0? No, it is 1 now. So repeat the same. Again check the value of these two numbers. Here Q1 and Q0 combination is 0 0. So before that we want to write this value just down here. Okay, here this is 0 0 again. 0 0 means what's the next operation? Just perform arithmetic right shift of AQ Q0 arrays without performing subtraction and addition. So perform this arithmetic right shift next. Arithmetic right shift of AQ Q0 array. Okay, so directly put this 1 here, keep this 1 here, then 1 1 0. Okay, next this 1 comes here, 0 1 1. Then this 0 comes here and discard this 0 value. And what's the next operation? Next operation is n equal to n minus 1. N equal to n minus 1. Okay, then how can we perform this one? Just 1 is reduced to 0 now. Okay, just write all other values directly down. Now check for the condition. If n equal to 0, n equal to 0 now. No need to repeat the same previous cycles. But the next step, if n equal to 0, our iteration is completed now and the result, final multiplication result is available in array A and Q. So, A and Q is this combination. This combination is actually our final result. Okay, check this value is correct or not. So, consider the sign bit. M must be bit of this A array. If it is 1, what's the meaning? If the MSB bit of A is 1, this means that our result is negative. If the MSB bit of this final A array is 0, this means our result is positive. Here this MSB bit comes as 1. What's the meaning? Our result is negative. Okay, so we want to put a negative sign here and then we want to find the magnitude value. If it is negative, then want to consider the 2's complement representation of this number. Okay, what's the number actually? 1 1 1 0 1 0 1 1. The 2's complement representation is 0 1 0 0 plus 1. This is the actual A array value and Q array value. Find the 2's complement representation 0 0 0 1 0 1 0 1. Okay, so this magnitude is actually 1 0 1 0 1 1 0 1 0 1. So convert into binary 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3 and 2 raised to 4. That is 16 plus this one, 4 plus this one, 1. 16 plus 4 plus 1 is 21 actually. So put 21 here and is already decided the sign of result as negative. How? Here the MSB bit of our A array after completing the iteration, check whether the sign is positive or negative. How it possible? If it is 1 in the MSB bit of A array, this means the result is negative. If it is 0 here in the MSB bit of A array, that means our result is positive. Okay, so put a negative sign. So if it is negative, then for getting the magnitude, we want to find the 2's complement representation of this AQ array first. After finding the 2's complement representation, convert into decimal, then we will get decimal equivalent of our product value. Once more, after completing the iteration, if the MSB bit is 1 here, that means our result is negative in sign. Okay, then in order to get the magnitude value, perform the 2's complement representation of this AQ array values bits, then find the decimal equivalent value. Then we will get minus 21 here. Suppose after completing the iteration, the MSB bit of A array is 0 here. That means our result is positive in nature. Okay, then what we want to perform? No need to find the 2's complement representation. Directly convert this A and Q array combination into decimal form. Then we will get the magnitude value. Is it clear? After completing the iteration, suppose our MSB bit of A array is 0. What's the meaning? Our result is positive in sign. Then in order to get the magnitude value, directly convert this AQ array bit into decimal representation, which will represent the magnitude of our result in decimal. If our MSB bit is 1 here, after completing the iteration, if the MSB bit is 1 here, what's the meaning? Our result is negative number. So if it is negative, then perform the 2's find the 2's complement representation of this AQ array first, then convert that 2's complement form into decimal representation, then we will get the actual magnitude value. Okay. Next, this is the hardware implementation part of our Booth's algorithm. This is the hardware implementation part. Multiplicand array, accumulator array and Q array. Here the last bit of this Q array is Q1 and a separate Q0 bit. Okay, so compare the value of this Q1 and Q0. Then here we have a control unit. This unit decide what to perform next, whether to perform addition or subtraction based on the value of this Q1 and Q0, or to perform arithmetic right shift of AQ Q0 based on the value of these two bits Q1 and Q0. Decide whether to perform an add operation at arithmetic right shift of AQ Q0, or want to perform subtract operation and an arithmetic right shift operation of AQ Q0. Okay. Based on this value of Q1 and Q0, a control unit decide whether to perform add operation or subtract operation, and after performing the proper addition or subtraction, place the resultant value back into accumulator array, then perform arithmetic right shift of AQ Q0 array. Then again check this Q1 Q0 value and decide whether to perform add or subtract. Then after that operation, write the result back into accumulator array, then perform arithmetic right shift of AQ Q0.